Welcome to the HBM Test and Measurement FAQ video series. Hi, I'm Bart Morick, HBM Application Engineer, and in this video I'm going to provide a short description of how a fiber Bragg strain gauge works. Metal foil strain gauges have been used in ESA applications for decades, but over the past few years another method has been found. Fiber Bragg grading sensors now have a place in the world of sensors, and they can be used as well as metal foil strain gauges in certain applications. So the question is, how does a fiber optic cable become a sensor? The process begins with etching a series of gratings onto the fiber optic cable. The gratings are basically a series of mirrors that are spaced a specific distance apart. The distance between the gratings allows each sensor to have a defined wavelength value. These gratings are created by inscribing or writing a systematic variation of the refractive index onto the core of the fiber optic by using an intense ultraviolet laser. Each fiber Bragg is tuned to a specific wavelength at which it will reflect back a portion of the light spectrum that is fed through it. As the light goes through the fiber optic cable, the majority of it is passed through, but a small amount is reflected back when the light gets to the FBG. The interrogator that supplies the light reads the wavelength of the light coming back, and we get a balanced result. When the fiber optic is strained, the distance between the gratings changes slightly, causing the amount of light to be reflected back to have a different wavelength. The interrogator reads back this change in wavelength, which is then converted into a strain value. Changes in temperature also affect the fiber Bragg grating so that they make a good thermocouple. A change in temperature present in the FBG causes the gratings to expand or contract, causing a change in the wavelength reflected back to the interrogator. One of the benefits of using fiber optic sensors is the ability to have multiple sensors in a single strand. Each sensor has its Bragg tuned to a different wavelength so that the interrogator can read back multiple values simultaneously with one lightweight cable, as opposed to a set of wires for each sensor as typically required for traditional strain gauges and other sensors. The one drawback to this is that a shift in opposite directions of neighboring FPGs could cause a wavelength overlap between sensors. If this happens, there's no way to separate the results from the two different FPGs, so it is important to plan the placement of your sensors carefully to avoid this possibility. There are a variety of advantages that fiber Bragg technology offers the user. With the ability to inscribe multiple fiber Braggs within a single fiber optic, you have multiplexing capabilities. The sensors can be used in multiple modes, such as one for strain gauge, another as a temperature monitor, etc. A long-distance transmission can be accomplished using fiber optic gauges because of the low loss you can expect. The sensors are impervious to large EMI events and are therefore can be used in high-noise applications that standard sensors cannot. The technology is immune to EMI RF signal and provides electric isolation since it does not have voltage or current excitation to power the sensors. The technology is stable over long periods of time, from days, months, and even years, and the size of the sensors are small and lightweight. So the fiber Bragg grating as a sensor is a good alternative for experimental stress analysis applications when a metal foil strain gauge just isn't practical. We hope that you take a few moments and download some application notes and spec sheets from our website to learn more of what these versatile sensors can do for you. Well, thanks for watching, and if you have any questions, please feel free to call, email, or visit our website for the latest product solutions and downloads at www.hbm.com.